In this video, we are going to continue our exploration of how to make really neat looking art from math, and in particular from trigonometry functions. Well, actually, we're going to diverge a little bit from the trigonometry here, but I will bring back some trig functions towards the end. All right, so the goal of this video is to create a logistic map. So what is a logistic map? First of all, if you don't know what a logistic map is, if you're not familiar with this term, please do not pause the video and look it up online. To be clear, the logistic map is something really amazing. It is a remarkable feature about chaos and mathematics and physics and biology. It's a pretty amazing thing that such a simple equation like this can lead to really complex dynamical results. However, the reason why I do not want you to look up the logistic map now is because if you are not already familiar with it, it is remarkably cool. It's really amazing to see what kind of picture we get when we plot this equation. So don't look it up yet and you will be surprised. And then after the video, I certainly encourage you to spend 15 or 20 minutes reading about the logistic map online. Okay, so the logistic map is basically created by solving this equation, by evaluating this equation. So let me walk you through what this equation means. So we have a vector x for n elements, so x is going to be n elements long, and n comes from the set of natural numbers that go from, well, technically they go from 1 up to 500. That's what the range that we are going to plot here. In Python, because Python counting starts at 0, this ends up being a little bit different. So n is actually going to start at index 0, but that's just an indexing thing. So n, basically we evaluate this equation 500 times, so we end up with a vector that is 500 points long. Okay, and then we start, so you see x n plus 1. So the next element in the vector x is defined as this parameter r times the current value of x times 1 minus the current value of x. So we need to set an initial condition for x, and I'm going to start with 0.5. So the first element in x, which in math notation you would write a subscript 1. Of course, in Python you would say the 0th index. So we start off with 0.5 and then we keep incrementing according to this equation. And now the value of r actually changes over different iterations. So we're going to loop over this equation and change r. We start off with an r value of 1, and then we increment r by a tiny little step and we get up to 4. We stop when r equals 4. So the way that you have to run this or implement this in Python is by having a for loop that goes through all these values of n to create the vector x for one value of r. And then when you've done that, you need to do another for loop that's outside that for loop to loop over different values of r. So I hope that makes sense. We need to first create vector x once for one value of r, and then we repeat that 1,000 times for 1,000 different values of r. And then what are you going to do? Well, what you're going to do next is for each value of r, so each iteration inside this for loop over the different parameter values of r, you want to plot the unique values in the last 10% of vector x. So what does that mean? Remember, vector x is 500 points long, although you can certainly experiment with other lengths, but for now we're just sticking with 500. So you need to find the last 10% of this vector. So that's for a vector of 500 points, the last 10% is just 50 points. So the last 50 points of vector x get plotted, only the unique values, so not the repeated values. The unique values of the last chunk of vector x gets plotted, and those values go on the y-axis, and the parameter r, the value of r, goes on the x-axis. And then you will see something pretty remarkable that you might actually recognize from various studies on chaos and dynamical systems. Okay, so I have to warn you, this exercise is a little bit trickier than most of the exercises in this course. So now is your chance to pause the video, give it a go, see if you can implement these instructions here, and see if you get a nice pretty looking graph. And now I am going to switch to Python, and I will show you my solution. All right, so we will need NumPy. So import NumPy as NP. And of course, we're going to do plotting. So import matplotlib.pyplot as plt. All right. So let's see. The way that I want to start here is by only thinking about that equation first. And then once I have that equation, I can start building it out more and more to the full assignment. So remember that equation was something like x plus, or x index n minus 1 equals the value of r times the current value of x times 1 minus the current value of x. So this is the basic equation that we need to work towards. So now I'm going to put this inside a loop. So we will say for n, that's the looping index that I'm using here. So for n in range, now I could just hard code this to be 500, but I'm going to leave this as a parameter n, and that's so that later on you can experiment with various values for n, so various sizes of this this vector here. Now this actually goes up to n, but because we actually want the vector x to have n points in it, so when we index n plus 1, we actually need this range to go up to n minus 1. And that's because at the last step, the last iteration inside this for loop, we are at n minus 1, and then little n plus 1, so big N minus 1, and then we are at the index little n plus 1, which is actually the same thing as big N. I hope that makes sense. Okay, so this needs to be tab indented. And now let's create some variables. So I'll say big N equals 500. I'm going to initialize vector x. So I'm going to say that this is, and initialize it to vectors, but actually remember I said that the first value of x, so the first value of x needs to be 0.5. So there's two ways to do that. We can say x0 equals 0.5, totally fine. This is a correct solution, but I think we can do this slightly easier and get rid of one line of code there. And I'm going to say 0.5 plus zeros. Now this is making the entire vector of x to be 0.5, but that's totally fine. It doesn't matter because as soon as we get in here, we are immediately replacing whatever all these values are. Okay, let's see. And I haven't yet defined r. I'll put that here. I'm going to say r equals 1. Obviously, we're going to have to create another loop over here. This is just, for making sure we get started. All right, so I'm going to press Control Enter. And we don't get any error messages. That's a good sign. And let's see what this looks like. So I'm going to say plot.plot, and I'll plot x and plt.show. Maybe I'll make this with little square lines. All right. So here you go. So we see that this looks like an exponential decay. So we start at 0.5, and this equation with the value of r set at 1, which actually is the same thing as not having any r here, basically just gives us an exponential decay. So before moving on, I want to try a few different values of r just to see what happens. So we see it starts at 0.5 and it goes down to 0. Let's see what happens when we set r to be 2. Oh, that's interesting. At r equals 2, it looks like we stay at 0.5 the entire time. We never leave a value of 0.5. I wonder what happens if we're a little bit, or halfway in between. Let's make r 1.5. So we still get this exponential decay, but it's steeper than it was before, and we're actually not getting all the way down to 0. It stays somewhere around 0.32 something. Okay, so let's see what happens when we do r equals 3. Oh, look at this. This is interesting. I'm actually going to get rid of these squares here. It doesn't help that much. Okay, so what's actually happening here is that there's no asymptote. There's no single value that this function is careening towards. It's actually bouncing up and down. It's going up and down like this. And in fact, so we can't actually zoom in here. So what I'm going to do, which I don't believe I've introduced you to in this course. So this is a bit of new information here. I'm going to write with a % here. So it's this kind of magical token here. I'm going to write matplotlib notebook. And now when I run this again, that's actually going to change the figure, And that's going to allow me to interact with the figure. And in particular, so we can, sort of move around the figure and things like that. But what I actually want to do is press this button, which is zoom. And now I can zoom in here. Now this is really interesting. We set this value of r to be 3, and all of a sudden this equation is no longer remaining fixed at a particular value. It's bouncing around, it's oscillating between these two values, something close to 0.68 and around 0.652 or so. Okay, so that is the basic idea. The point is, you can see that this equation is giving a different result. This also looks pretty interesting, depending on the value of r. So that's why we now want to create a loop that goes outside this loop to evaluate for different values of r. Okay, so let's do that. So we need to say, I'm going to say rs here for r's, and that's going to be linearly spaced numbers between 1 and 4. And remember, we want 1,000 of them. Okay, so then we need another for loop in here. So this is going to say for, I'll set this looping variable index to be ri, for the ith index into r. So for I in, now we want to loop over the number of elements in rs. So for I in range of the length of rs. Now here you also could have hard-coded this to be 1,000, which is kind of okay, but if you leave this soft-coded to be the length of rs, then that allows you to basically, experiment around with different lengths of r. Of course, you could also set this parameter to be a variable, the way I set n here to be a variable, as you like. Okay, so let's see. So inside this loop, now we need to change the value of r. We need to update r. So r is going to be the rith element in this vector rx. Now, of course, we need to tab indent these two. And let's see what we got. So we have all of this. We're looping over all the values in r. And, oops, that needs to be, oh no, this doesn't need to be changed. Although, actually, I think I will. So what I'm going to do is cut this and paste this in here. So now I actually don't need to create this separate variable for r. Okay, so now we're getting closer. I didn't actually, not plotting anything in here. We're not getting the unique values from the last 10% and so on. But I'm still going to run this because it's always a good idea to run your code after writing just a few lines of code, just to make sure that you haven't created any errors or warning messages or anything like that. Okay, so this is actually the final value of x. So this is the vector x when r equals 4. And looks like we've broken out of that steady state, at least temporarily. So we no longer get these oscillating sequences. It just flattens out at 0. All right, pretty cool. So we are getting there. What I'm going to do next is add this part where we find the unique values in the last 10% of x. So what I'm going to do is create a new variable. I'm going to call this ncap. And that's going to be numpy.arange. And this is going to go basically from something from the last 10%, which I'll call n times 0.9, up to n. So this is going to give me the indices of the last 10% of the vector x. Now, the problem here is that the last 10% might not necessarily be an integer value. For example, let's say we test n equals 501. And in this case, this is not going to be an integer, which means we are going to get an error here. So what I'm going to do is say numpy.round. You could also use the int function if you like. Basically, we just want to make sure that this is going to be an integer, even if n times 0.9 is itself not an integer. Okay, so then what we need to do is, and we need to be careful about the spacing because we don't want to find the last values of x inside this loop because we're still creating x. We want to define the, or identify the last 10% of x inside this loop, but outside this loop. So in fact, we need to have spacing that looks like this here. So I'm going to call this u, this variable u. So we get x and then end cap. So you see this is going to be the last 10% of all the values in X. So, and then I'm putting them in U. Now, there's going to be a lot of repeated values in variable U. You can see that here. These values are all basically 0. You can see actually they're not exactly 0, but they're pretty close to 0. Actually, no, these numbers down here are telling me the coordinates in the plot. I believe all these values are in fact exactly 0. Nonetheless, okay, so what we need to do is find the unique values here. So I'm going to use numpy.unique. And I don't remember if I've introduced you to this unique function yet. So I'm just going to take one moment of your time to illustrate what this unique function does. So let's say 1, 1, 2, 2, 3. Okay, so that's just a list of numbers. And now I can say numpy.unique like this. And now we only get 1, 2, 3 because this 1 is repeated, this 2 is repeated. All right. So now we have our unique values of X. And now we also need to have a repetition of R. So basically what we want to do here is say plt.plot R comma U. And we want to make these little dots. So U we already have, these are the Y values. And now R, these are the X coordinate values. And actually R is just this value of RS. So it's just like this. However, this is actually just one value, and this is going to be, well, whatever it's going to be, some number of values. Actually, for this last value of R, it's still going to be one value. U, vector U, will have only one value, which is 0. But for other values of R, U is going to be bigger than 1, a vector of length more than 1. So we need to say, so we need to basically repeat this individual value. So I'm going to do this by creating a vector of 1s of length U, and then they all get multiplied by this value of R. And we don't need to plot X anymore. All right, are you ready? Let's see what this looks like. Well, it looks like an error. Okay, so the problem here was actually with the round function. So numpy.round is actually still returning a floating point decimal. So still with a floating point number, so still with a decimal point. In fact, what we wanted was just the built-in round function, which will return an integer. Let's see if this works now. All right, this is working, it's running. And look at that, this is super beautiful. Isn't this amazing? These are called bifurcations. So you have this upward slope here, and then you get a bifurcation, and up here at R equals 0.347, I forget the exact value that this bifurcates. You get another bifurcation and more bifurcations and more bifurcations, and you get to just total chaos. So let me change these dots a little bit. I'm going to make them, let's make them black dots, and I'm going to set the marker size to be 1. All right, and then let's see what this looks like. This is a little bit more interesting. Of course, you can increase the resolution of R. You can make the dots a little bit smaller, and that gives you a slightly better picture of what's going on here. But there's so many fascinating things about this plot, and I'm not going to tell you about them in the interest of time, because there's 2 more things that I would like to do with this code before closing out this video. One of them is to change the colors of this. So these are all black here, but what I want to do is change the color gradient so that the colors are changing as we move through different values of R. And what I'm actually going to do is copy and paste this from somewhere else, from my other secret monitor where I have my cheats, my answers. So I'm going to get rid of this black color. And here I set the color to be basically a sine function of red, a linear function of green, and constant value of blue. And that's just some random color combination that I played around with, and I like it. So you can see it goes from green, and then it transitions through this kind of reddish color, and it turns into purple. Obviously, I encourage you to play around with these color values and try and get something that looks nicer than my plot, and then share it on the Q&A forum so I can compliment you on doing a better job than I did. All right, one last thing I want to do. It's only going to take a minute. Now, this section of the course is called Art from Trigonometry. Where is the trigonometry? There's no trigonometry anywhere in this code yet. So what I'm going to do is add a little bit of trigonometry. So to the end of this function, I'm going to add a sine, and this is going to be some periodic function, so 2 pi times x of n, and then it's actually going to be sine squared. Now, it turns out that this is a little bit too strong an influence of a sinusoid on this vector x. So I'm going to scale this down by a value of 2. So here's what it looks like without the sine addition. And here's what it looks like with the sine addition. You can see we get some interesting little offshoots and these really interesting just chaos dynamics. So this is an example of a dynamical system that produces some balance of order. So there are certain regimes of this parameter r where we get a very ordered response, and there are other values of r where we get a chaos response. It turns out that as you go further up in r, we oscillate between periods of chaos and periods of order. Well, I hope you enjoyed working through this lecture and discovering the logistic map and how to parameterize a logistic map. Now that you're finished with this lecture and you see what kind of wacky dynamics you can get from a really simple equation, I encourage you to take a break from this course, spend a little bit of time on the internet to read more about logistic maps and how they are used in physics and mathematics and in biology.